Section: Contents. In this section, we discuss the growing interest in enabling multimodal large language models, MLLMs, to incorporate visual inputs into their reasoning processes. We identify two main approaches to achieve this. The first approach involves generating images to assist reasoning, which is useful for tasks that require imagination, like solving math problems. However, the quality of these generated images can be poor, leading to a loss of important details and increased computational costs, which slows down real-time applications. The second approach focuses on cropping, where the model selects relevant parts of an image, typically using bounding boxes. While this improves accuracy and reduces errors, it is limited in functionality compared to models like OpenAI's O3, which can perform a variety of operations beyond cropping. To address these limitations, we propose a new framework called Think Beyond Images, or Thyme. This framework is based on four key principles. 1. Rich functionality. Thyme supports various image operations, including cropping, scaling, rotating, and enhancing contrast, as well as complex mathematical tasks. 2. High autonomy. Thyme can independently decide which image operations to perform and generate the necessary code without human input. 3. Efficient end-to-end training. We use a supervised fine-tuning and reinforcement learning approach that requires only 200 GPU hours to unlock the model's capabilities, with reinforcement learning further enhancing these abilities. 4. Significant and stable performance gains. We evaluate Thyme across nearly 20 benchmarks in perception, reasoning, and general tasks, showing consistent improvements in all areas. To implement this vision, we focus on several key components. SFT data construction. We create a high-quality dataset of about 500,000 samples from over 4 million sources, covering various scenarios like image operations, cropping, and complex computations. SFT training strategy. We employ specific training methods to ensure effective learning, such as masking outputs during loss calculations and using techniques to activate the model's capabilities. RL data construction. Our reinforcement learning dataset includes both filtered open-source data and 10,000 manually curated high-resolution images to enhance the model's perceptual skills. RL algorithm design. We introduce a method called GRPO with adaptive temperature sampling to improve code generation by adjusting sampling temperatures for text and code. Sandbox design. We create a secure environment for executing model-generated code, which simplifies the coding process and improves usability. Thyme effectively combines high autonomy with rich functionality, allowing it to assess problem complexity and autonomously perform multiple operations. The training phase is efficient, requiring only about 200 GPU hours to enable various image manipulations. Our evaluations show that Thyme outperforms existing models in perception, reasoning, and computation tasks. We plan to open source the complete dataset, sandbox environment, and training code to support further research and community adoption. Section summary. In this section, we introduce our novel paradigm, Think Beyond Images, Thyme, which enhances multimodal large language models by enabling rich image operations and high autonomy in decision-making, all while maintaining efficient training processes. We demonstrate that Thyme achieves significant performance improvements across various perception and reasoning tasks, supported by a comprehensive dataset and a secure sandbox environment for executing model-generated code. Section: Overall pipeline of Thyme. In this section, we outline the overall pipeline of Thyme, which consists of two main components, the model and the sandbox. When we receive user input, the model first analyzes the problem to determine if code generation is necessary based on the problem's type and difficulty. If the problem is simple or has been addressed in previous interactions, we provide the answer directly. However, if code generation is needed, the model autonomously creates the code. Our training data includes various image operations like cropping, zooming, rotation, and contrast enhancement, and the model can combine these functions in its code. The model decides on input parameters, such as the contrast factor and crop coordinates, without external constraints. The generated code is executed in a secure sandbox that handles the code and returns the results. We use Python's built-in modules to format the code, correct variable properties, and fix parameters, ensuring functionality while minimizing errors. For the sandbox, we prioritize security and robustness. We prevent unauthorized operations that could harm the system and set a maximum execution time of 10 seconds to avoid long delays. To ease the model's coding burden, we use tools like AutoPep8 for formatting and the AST module to identify cropping parameters. We also preset local variables and check for newly created variables after execution to ensure everything runs smoothly. Additionally, we keep track of variable dependencies across multiple code segments to maintain context. Next, we discuss the cold start of Thyme, focusing on our data construction and training strategies. We categorize our training datasets into 3 levels of complexity. The first category involves tasks that can be answered directly without code. The second includes tasks requiring image operations and computations, while the third involves multi-turn interactions for complex problems. We source our prompts from various open datasets to ensure diversity. For the simplest tasks, we train the model to bypass coding and provide direct answers. We select 100,000 samples from the LLAVAOV image dataset for this purpose. For more complex tasks requiring code, we rigorously verify samples in our sandbox, discarding non-executable codes and ensuring the model meets its goals. 2 multimodal experts further screen the data, resulting in a refined collection of 50,000 high-quality QA pairs. To supplement real-world data, we manually create additional datasets, ensuring consistent quality through similar verification processes. We also develop specific coding datasets for cropping, rotation, low contrast enhancement, and computational tasks, yielding thousands of high-quality samples. Finally, we recognize that models trained on single-turn interactions struggle with error correction. To address this, we create multi-round conversational datasets that teach the model to analyze past execution results for better accuracy. This includes refining results based on feedback and correcting mistakes from earlier steps, enhancing the model's ability to improve its image manipulation tasks. Section Summary. In this section, we describe the overall pipeline of Thyme, which consists of a model that generates reasoning processes and a sandbox for executing code securely. We detail the training data construction for various task complexities, ensuring high-quality datasets through rigorous verification and manual curation to enhance the model's performance in image processing and multi-round interactions. Section: Training Strategy. In this section, we outline our training strategy. We present our system and user prompts in tables. The system prompt clearly defines the task format, expected code style, and how to present execution results, ensuring the model understands what is required. The user prompt provides the image path and size, which helps with loading images correctly and avoiding errors. It also specifies the desired output format. We formalize the training process of Thyme to clarify our training techniques. Given an image and a question, the model generates a sequence of thought processes along with optional code. If code is produced, it is executed in an external sandbox, which returns results that could be images or numerical values. The model interacts iteratively based on previous results until it arrives at a final answer. Each training sample is represented as a combination of the image, question, and the sequence of thought processes, code, and results. During training, we faced several challenges. First, in 2-round dialogues, the model often produces incorrect or incomplete analyses in the first round, which are corrected in the second round, making the first round less useful. Second, there is less math data compared to image data, which hinders the model's ability to generate computation-related code. To tackle these issues, we implemented several strategies. 1. Train on the last round only. For samples with multiple rounds, we focus only on the last round's content, masking out earlier rounds to ensure the model learns from the final outputs. 2. Sandbox content exclusion. we exclude sandbox identifiers and execution results from training targets, preventing the model from learning to predict these outputs directly. 3. Math data annealing. We first train on image data and then fine-tune on math data with a lower learning rate, allowing the model to learn all rounds together during this phase. Next, we discuss the construction of reinforcement learning (RL) data for time, which includes selecting data from public datasets and manually creating complex visual question answering data to increase task difficulty. For RL data construction, we curate data from various sources, ensuring that questions and images are relevant. We also address the limitations of publicly available datasets by manually collecting 30,000 high-resolution images, each with significant dimensions to enhance complexity. A team of annotators labels these images, creating challenging questions that require zooming in to identify small objects. The questions cover various aspects, such as recognizing text, attributes, positions, quantities, and object categories, as well as understanding charts. All annotation data undergoes thorough cross-checking and is reviewed by multimodal experts to ensure high quality. Section Summary. In this section, we outline our training strategy for the Thyme model, which includes defining clear prompts for task execution and addressing challenges such as ineffective initial dialogue rounds and imbalanced data types. We implement strategies like focusing on the last interaction round, excluding sandbox outputs from training, and fine-tuning with math data to enhance performance, while also detailing our approach to constructing and annotating complex visual question answering datasets for reinforcement learning. Section. Preliminary of Reinforcement Learning Algorithm. In this section, we describe our approach to the reinforcement learning algorithm. We utilize a fully on-policy version of the Group Relative Policy Optimization (GRPO) algorithm. For each task, which includes an image and a question, we sample a set of interaction sequences from our policy. Each sequence represents a complete interaction, consisting of the image, question, and a series of actions and responses. We update our policy by maximizing a specific objective that includes a term penalizing significant deviations from a reference policy. The total number of tokens generated in each sequence is calculated by summing the lengths of the text and actions produced. The advantage for each token is determined based on the final rewards from all sequences in the group, normalized by the mean and standard deviation of those rewards. We also implement adaptive temperature sampling in our GRPO. We recognize that code generation and textual reasoning require different sampling strategies. For code generation tasks, which follow predictable patterns, we set the temperature to 0 to ensure precise outputs. In contrast, for natural language reasoning, we use a temperature of 1 to promote diverse responses. Our system dynamically adjusts the temperature. It drops to 0 during code generation and returns to the default setting afterward. Through our experiments, we observe two key advantages. First, adjusting the temperature improves sample efficiency, allowing previously unusable samples to become valid. Second, it prevents the model from becoming overly cautious and avoiding code generation altogether, as lower temperatures help maintain the usability of generated code. Section Summary. In this section, we describe our implementation of a fully on-policy group relative policy optimization (GRPO) algorithm, which updates the policy by maximizing a specific objective while penalizing deviations from a reference policy. We also introduce adaptive temperature sampling, setting the temperature to 0 during code generation for precision and to 1 for natural language reasoning, which enhances sample efficiency and prevents the model from avoiding code generation due to error-prone outputs. Section. Sampling Optimization. In this section, we address the challenge of sampling optimization in our multi-turn interactive task. The limited number of interaction rounds creates a strict time budget for sampling, as lengthy or repetitive dialogues can lead to increased computational costs. When our model makes repeated errors, it generates redundant outputs, wasting resources on invalid samples. To tackle this, we implement an early termination mechanism during training. We use the Rabin-Karp rolling hash algorithm to track occurrences of fixed-length substrings in the model's output. If any substring appears so often that its total length exceeds half of the entire output, we mark it as repetitive and stop the sampling for that instance to save computation. Additionally, we set a manual limit on the maximum number of dialogue turns, referred to as max iterations. If dialogues exceed this limit without ending, we truncate them to manage context length and enhance training efficiency. Next, we discuss our reward function design. For formatting reward, we require the model's output to follow a specific structure, using less than think greater than less than, think greater than tags followed by less than answer greater than less than, answer greater than tags. This structure encourages the model to reason before providing a final answer, enhancing interpretability. For result reward, since not all answers are strictly numerical, we first use a rule-based method to compare the model's output with the correct answer. If this fails, we employ an auxiliary model, QWEN 2.5 VL72B, to assess semantic equivalence and correctness. This hybrid approach improves scoring efficiency for open-ended questions. The consistency reward checks if the final answer logically follows from the reasoning steps, ensuring coherence. However, we must be cautious, as high consistency rewards could lead to incorrect answers being favored. To avoid this, we define the final reward by combining the result reward with a consistency bonus, but only if the answer is correct, thus preventing an overemphasis on consistency at the cost of accuracy. In our experimental setting, we outline our hyperparameters. Our training is divided into 3 stages. The first stage, Thyme SFT, starts with training on image manipulation data, followed by mathematical code data. We set learning rates for these phases to 1 × 10 to the power of -5 and 1 × 10 to the power of -6, respectively, while keeping other hyperparameters consistent. The batch size is 128, and we train for 3 epochs, using the final epoch's checkpoint to start the next phase. The warm-up ratio is set to 0.05. In the reinforcement learning stage, we use a learning rate of 5 × 10 to the power of -7 and train for 1 epoch. The KL divergence coefficient is set to 0.001, with a batch size of 256, 4 rollouts, and a repetition penalty of 1.05. We choose Qwen 2.5 VL7B as our backbone and conduct all training on 32 NVIDIA H800 GPUs, totaling about 224 GPU hours. The annealing stage takes around 8 GPU hours, while the reinforcement learning stage requires over 1,200 GPU hours. For benchmarks and baselines, we select 3 main categories. The first focuses on perception tasks, as Thyme's image operations aim to enhance perception abilities. We include benchmarks like the Me Real-World Series, HR Bench, V**, and Real-World QA, reporting results for different splits. For instance, we report perception and reasoning accuracy separately for the Me Real-World Series. The second category involves reasoning tasks, as Thyme can also transform complex computations into code. We use benchmarks like MathVista, MathVerse, LogicVista, WeMath, and VisuLogic to evaluate reasoning ability. The third category includes general tasks to assess overall performance improvements as perception and reasoning abilities grow, with benchmarks like Hallucination Bench, MM*, MM*VetHard, OCR Bench, Chart QA, and Blink. For baselines, we use QWEN 2.5 VL7B as our primary comparison, alongside other models like Intern VL3-8B and larger models such as QWEN 2.5 VL32B and GPT-4o. We ensure fair comparisons using the VLM Eval Kit evaluation pipeline. Section Summary. In this section, we address the challenges of multi-turn interactions by implementing an early termination mechanism to prevent redundant outputs and control computational resources, alongside a structured reward function that balances formatting, result accuracy, and consistency. We also outline our training procedure, benchmarks, and baselines, emphasizing the evaluation of perception and reasoning tasks to assess the model's performance effectively. Section: Evaluation Results. In this section, we present our evaluation results, focusing on the main findings. We provide a detailed comparison between our model, Thyme, and other top multimodal models across various benchmarks related to perception, reasoning, and general tasks. In perception tasks, Thyme shows clear advantages, even when compared to larger models like Qwen 2.5-VL32B, suggesting that simply increasing model size does not effectively solve perception issues. Instead, our test time scaling strategy significantly enhances performance in these tasks. Additionally, by transforming complex computations into executable code during training, Thyme improves its reasoning abilities. However, we note that in reasoning tasks, the benefits of scaling model size are more evident, indicating that reasoning skills depend heavily on the model's internal knowledge. Thyme primarily boosts visual recognition and prevents the model from making overly complex predictions independently. As a result of these enhancements in perception and reasoning, Thyme achieves notable improvements in many general tasks, particularly reducing hallucinations. Focusing on perception tasks, we use Me Real-World as an example, which includes high-resolution tasks in real-world settings. Our results show that for tasks where the baseline model performs well, like OCR and diagrams, Thyme's improvements are limited. However, for more challenging tasks, such as monitoring and autonomous driving, Thyme outperforms the baseline by over 25% in both perception and reasoning, with reasoning improvements being particularly significant. Next, we examine the impact of different training strategies during the SFT phase. We compare several approaches, as detailed in our results. The naive SFT method uses all data without any strategies, resulting in chaotic outputs and limited performance gains. The mask sandbox strategy, which masks sandbox labels and outputs, allows the model to focus on writing code and reasoning based on results, leading to significant performance improvements. The only last round strategy masks earlier round information, helping the model avoid learning incorrect patterns. We also explored the effect of removing comments from the code during training, finding that this negatively impacted performance, as comments help the model understand the code better. Lastly, we addressed the small volume of mathematical code data, noting that while mixing it with the full dataset did not yield significant gains, it did help the model learn to use code for complex calculations. In the next subsection, we discuss the influence of reward design on the RL process. We summarize various reward strategies and the challenges we faced. In addition to format and outcome rewards, we introduced consistency, code, and process rewards. The consistency reward assesses the alignment between reasoning and final answers, while the code reward encourages the model to produce correct and functional code. The process reward evaluates the quality of the reasoning process. All additional rewards apply only when the model's answer is correct, ensuring that the model prioritizes solving problems accurately. Our findings indicate that the consistency reward consistently improves performance, while scoring the reasoning process increases computational demands but can negatively affect performance due to its subjective nature. We also observed that the code reward encourages the model to generate more code, but this code is not always necessary for solving the problem, leading to no positive performance gains. Section Summary. In this section, we present a comprehensive evaluation of Thyme, highlighting its superior performance in perception tasks compared to larger models, and its effective training strategies that enhance reasoning abilities. We also discuss the impact of various reward design strategies on the reinforcement learning process, noting that while consistency rewards improve performance, other rewards may introduce challenges without significant gains. Section: Analysis of the RL learning process. In this section, we analyze the dynamics of key metrics during the reinforcement learning (RL) process, leading us to several important observations. First, we notice that the average response length decreases quickly at first and then levels off. This drop is due to the supervised fine-tuning (SFT) phase, where we use a lot of synthetic image operation data to help the model learn code generation for solving problems. However, since the images are often simple, many coding tasks become unnecessary. During the RL phase, the model realizes that for most tasks, providing a direct text response is more effective than generating code, resulting in a quick reduction of unnecessary code generation. Next, we observe that the result reward generally trends upward, which is what we expect from a successful learning process. A more striking finding is related to the consistency reward. At the beginning of training, the average result reward is around 0.5, while the average consistency reward is only 0.15. This gap shows that many initially correct answers lack solid reasoning, emphasizing the importance of the consistency reward. By adding this reward, we encourage the model to ensure its reasoning aligns with its final answers. As training continues, the result reward rises to about 0.7, and the consistency reward increases to nearly 0.35. This indicates that incorporating the consistency reward significantly reduces contradictions between the model's reasoning and its responses.